Hey guys, I know there wasn't a lot of really demand for this video, which is okay, because this homework was a little bit easier than yesterday's. There weren't as many problems and it was a little simpler after more practice. But I'm going to make this anyway, because I'm going to cover number 3 and number 5, because there are some unique things that show up on each of those, and I wanted to go over that, because as I've said, and I know a lot of people find this kind of annoying, but I do believe it, it's what I follow, is that math is more about understanding why something happens more than memorizing exactly what is going on, because that'll help you do more difficult problems like Ms. Poole often puts on our tests. So that's why I'm doing this. So we're going to start with number 3. I don't have a grid of it since I have it on the whiteboard, but I'm going to tell you the points that she had, and you can look on your worksheet if you want. So this is about what she gave us. This point was at about 8, or it was 8. So we have 8 here. This point was at 2, and we could pretty well see that there was an asymptote here that went through y equals 2. So this is what we have. We have our asymptote, we have our 0, and we have our y-intercept. So the first thing I do is I look at all the information that we have, and we can see the first thing that's pretty clear is there are no removable discontinuities or vertical asymptotes. So we can immediately see no discontinuities, which make it easier, so we know that our denominator won't have anything with roots. So now we can look at things in the numerator like x-intercepts, and we see the only one we have is at 2. And we can also see that since it bounces off of 2 instead of crossing the x-axis, then it must be an even root. We don't necessarily know it's a double root because it could have power of 4 or something like that. So we can just write even root. Right? So the last piece of information that we have is this asymptote here, and we can see it's not at 0, which means that the degree of the numerator can't be less than the degree of the denominator, because as it gets larger, it won't approach 0, because the bottom won't get infinitely larger than the top will as you get, or the denominator won't get infinitely larger than the top numerator will as you get to really big numbers. So if we see that it's constant, since we have a constant function as our asymptote, it means the top and bottom must be of the same degree. So we see num degree equals denom degree. And we can also see that since we've kind of played around a lot with rational functions, and if we're going to leave this in factored form, since we don't have to expand it out in factors form is always easier, we can also see that the a value is going to have to be 2, because if you have the same degree in the top and the bottom, then say if you had, for example, x squared plus 7 over x squared minus 6 plus 1, or 6x plus 1, as you get to really, really big numbers, this 7 will become negligible, right? Because like a billion squared plus 7 is about the same as a billion. So our asymptotes come in. In the bottom, both of these will also become negligible as you get really big, because they're so much smaller. And so you just get x squared of x squared, and it would approach 1. But since we're approaching 2, that means that, say, these aren't actually factors, but suppose they were. If these are the 2 factors that you have, then if it's approaching 2, instead of 1, there must be a 2 in the numerator that will allow this to approach the asymptote of 2 instead of 1. So we can determine, we know that the degrees are the same from the asymptote. We can also say that a equals 2. Alright, so we got pretty much most of the information we can out of the graph for now, so we can go ahead and start writing the equation. So f of x equals, we know there's 2, we know there's the root in the numerator, x minus 2, and since we don't necessarily know that it's a double root, but since this is like our first homework doing this, we can pretty much assume it's a double root. And if we have if the denominator doesn't really have any restrictions on, because there are no asymptotes, you don't necessarily have to have a single root or a double root or anything like that. We can just go ahead and write as a double root, because Ms. Poole did say that there are multiple answers to this. So maybe there is a way to write this with a 4th root, and there actually is, but we won't talk about that. So we can go ahead and assume this is a double root. And if we do run into problems with double roots, we can always go back and try a 4th root, but we're going to start with a double root. And so those are the only zeros, so that's all we put in the numerator. So the denominator is where it gets a little tricky. This is the kind of the interesting thing that happens with this problem. So we know it has to be something of degree 2, because these are the same degree, and we know it can't have any rational roots, because then there would be a discontinuity, and there aren't any. So we're left with, the way I did it, as I just wrote it as C, which, let me explain. So where C represents a quadratic expression with no real roots. So that's a way to think about it for now. And since we do have more information to analyze, we can leave it like that. And so a way that you could think about this is quadratic expression with no real roots. An easy way to think of one is x squared plus anything, because obviously x squared, you can't factor x squared plus a number, because x squared will always be positive. So if you add another number, then that'll always be positive, and there's no value that you could plug in for x that would allow the numerator to be 0 or negative. So that'll make it pretty easy, or no real value that you can plug in for x. So something like x squared plus c would be an easy case. And again, there are a lot of different ways that you could come up with this. There's not necessarily one formula for this function. So you could also write something in the form ax squared plus bx plus c, where it just fails the discriminant test. But we're just going to do this for now because it's the simplest. So we can, since we know this is a simple term and it could possibly work, we're going to try plugging that in. So x squared plus c in the denominator. And so we have the right a, the coefficient of x squared is 1, so this, we can factor the 2 out if we need to make sure that a is 2. So that's good. We have our numerator and denominator at the same degree, so that's good. Now we just need to figure out what c is. And to do that, we use the one piece of this graph that we haven't touched on yet, and that's the y-intercept. So we can just plug in, as we did yesterday, if we plug in 0 for the x value, we know it's going to equal 8, because that's the y-intercept. We also know it's going to equal 2 times negative 2 quantity squared over 0 plus c. So now we can just solve for c. So 8 equals 2 times negative 2 quantity squared is equal to 8 over 0 plus c is clearly c. And then we can deduce from this that c equals 1. And so now we know what c is, and we can write our final equation. There we go. This is what Ms. Poole had on her key. And like she said, there are lots of different things that you could possibly have. The things that have to be important is you have to have the x minus 2 with some even power. Whatever the power of this is, then that has to be the degree of the denominator as well. And the only a value, or the only a value has to be 2, which means that if you were to take out, you could still have anything for the denominator, like you could have a coefficient of 3, but if you did have something like that and you factored it out, and you had any coefficients for the numerator and the denominator, and you factored them both out, then the ratio of those has to be 2. That's the only important thing. It doesn't necessarily have to be only 2 in the numerator. And we just have to make sure this has the same degree as this, and anything like that could possibly work. So this is probably the simplest case, and I know Sai also talked about this some on the discussion page, so you can go read that too, because Sai is a very intelligent individual. Alright, so there's number 3. If you guys had any other ideas about ways that you could solve this, or something I didn't think of that's more creative, then please let me know. That'd be cool to know. Could be helpful, because again, it's about thinking about the way that it works rather than just memorizing how. So I'm going to cut away for a minute as I draw number 5. Alright, I'm back with number 5. I drew it, again, I don't have a grid the way Miss Poole's homework does, but I approximated, and we'll get into a little bit how her grid eye is actually pretty helpful. But we're just going to leave it like this for now, and I'll talk about it, and again, you can have your assignment with you and just refer to it, because I don't want to draw a whole like 20 by 20 grid, because that would take a long time. So we're going to start with this, and again, we can start with asymptotes or discontinuities, or removable discontinuities, and we can see there are no removable discontinuities, but there is one vertical asymptote, and it's right here, and you can tell pretty clearly on the graph that she gave us that it's about at x equals 1, we're just going to stick to that. So there's our vertical asymptote. And we can also see that since it approaches both sides of the asymptote on the positive end, that means that there's no sign change. So it's going to be an even root when this is in the denominator. And remember, it's not necessarily a double root, but we may use a double root for our purposes since we're just looking for a simple form. We're going to say even root. So there we go. That's all the stuff we need to know about our denominator for now, because there are no other discontinuities. Now for the numerator, you can see this point on the grid. We can see it was -2, and we also have this point here, which is at the origin. Those are only x-intercepts, and again we see this has to be an even root because it bounces off the axis instead of crossing it. So even root, but we see at the origin it does cross the x-axis, so it's an odd root. Alright, so we have our numerator, we have our denominator. Now we can go ahead and look at end behavior. So this is a little different because it doesn't have a constant asymptote. It has a slanted asymptote, which I'm sure all of you noticed, and it's about along here. And what's actually very helpful is, this is where her graph came in helpful, is you can sort of approximate that next to each point, or next to the graph, there's a point on each end. There's a point down here that was, I believe it was -22, -8. And there's a point somewhere up here that was 22, 14. And that's, again, it's an approximation, but it's a very good approximation since it's right next to the graph. So we can go ahead and figure out what the function, or the rule of this function would be, and since it's obviously linear function. We know it's first degree. We can calculate the slope as delta y over delta x equals 22 minus negative 22 over 14 minus negative 8 equals 22 plus 22 is 44, 14 plus 8 is 22, and it's 2. So if something as easy as that's backwards, it's actually, this is the x, this is a y, okay. So that should be flipped, my bad, flipped. It should be 1/2. Yep, easier to take a mistake, try to avoid those. So we see something that's as clean as this, we can probably assume that's what it's supposed to be approximated towards on her graph, because I'm guessing she's not going to give us something weird like 21/44, that would be kind of mean. So we're just going to stick with this. So that's the slope. Now since we have, say, a point here, or a point here, we can have, just plug it into a linear equation. So 14 equals the slope times the x value plus the y-intercept, wherever that hits. And we can just solve for b and find that b equals 3. So there we go. So the function of this asymptote is y equals 1/2 x plus 3. So there we go. And she also gave us the point 4, 8, which was right here. I forgot to mention. And Henry actually noticed that he mentioned in our class discussion, if you want to go look at it, that you can solve it either way. You don't necessarily need this point and the function of the asymptote. There are 2 different ways to do it, and I'll do both, just to kind of clear up that it does work both ways, and you don't necessarily need both of them, and you're not missing any information if you only do it one way. It's just a good way of checking. But it's also kind of cool how you can do this and kind of reverse engineer the way that you find asymptotes, because I talked about yesterday the long division to find the asymptotes. We're going to touch on that a little bit. So if we go ahead and start writing our function, we have f of x, and also, since we see that this is a constant, or not a constant, a linear function, the asymptote, that means that the degree of the numerator is going to have to be 1 more than the degree of the denominator, because we talked about if they're the same degree, then you get a constant function. So it would make sense that if it is 1 degree higher on the numerator, then after you do long division, you'd have a linear asymptote. So we're going to stick with degree of num equals degree of denom plus 1. So, for example, like the numerator could be cubic and the denominator could be quadratic, something like that. So, now that we have all that information, we can go ahead and start writing this. So, we don't yet know our a value, so we can just write a for now. So for the x-intercepts, we know we have an even root at -2 and an odd root at 0, and we're going to go ahead and do the most basic exponents for that, because again, you could try a lot of stuff, but this just seems the most simple way since she doesn't care for a specific answer. So we're going to start with just x plus 2 squared, since that's the even root, times x, since it's at 0, the origin. And again, the y-intercept is at the origin, but that won't be much help, since we already know that we have an x-intercept there too, so we can't really use that to solve for a. So that's where it gets a little bit annoying here, but that's okay. We have this point, and we have our slope, so it'll be alright. So the denominator, we have x equals 1, that is the asymptote, and again, it's an even root because the sign change there is no sign change up here. As it goes positive, comes back positive. So again, since we already have a degree of 3 in the numerator, because we have a second degree here times a first degree gives us a third degree. We know that the denominator has to be second degree, so we can just write this as squared. So we have x minus 1 quantity squared. So this is what we have now, and we need to solve for a, and the quickest thing I would think, and everyone would probably agree, is to just plug in the point. So if we do that, we get f of 4 equals 8 equals a times 4 plus 2 is 6 quantity squared times 4 over 4 minus 1 is 3 squared. So 8 equals 36 times 4 is 144 over 9 times a, and this simplifies to 16, so 8 equals 16a, so a equals 1/2. Now we're pretty much done, so that was pretty easy. Equals x plus 2 squared times x over 2 times x minus 1 quantity squared. And that is the answer that Ms. Poole had on the solution sheet. So that is a pretty easy way to do it. But I'm also going to go over how you use the asymptote to solve it. Alright, so as we talked about yesterday, when you do long division, the actual, everything that's not the remainder will be the end behavior asymptote. So we can immediately say that if we divided, and we're still going to use this form up here with just a, since we already figured everything else out without the asymptote or this point. So we can do x, or excuse me, and again, I talked about this yesterday also, we want to expand instead of leaving in factored form when we're doing long division, because it actually makes it a lot simpler. So if we expand the numerator, we get ax cubed plus 4ax squared plus 4ax. You can check that if you want. And the denominator, we get x squared minus 2x plus 1. So we have this. This is how we're going to solve for long division. And we can also determine that since this is our asymptote, that when we actually do this, we'll end up with something in the form of, where did I write it? Right down here. 1/2 x plus 3 plus c over x minus 1 squared. And this part is going to be the remainder, but we don't really care about that. I'll show you why. We only care about this part. And yeah, so we're just going to stick with that. So when we do long division here, x squared needs to go into ax cubed, so we get ax. So we subtract ax times x squared is ax cubed minus, ax times 2x equals 2ax squared, and then plus ax. Subtract that, and these cancel. We get 6ax squared plus 3ax. Now to get x squared to go into 6a, we do plus, or 6ax squared, we get 6a. Subtract that again, 6ax squared minus 12ax plus 6a. Cancel these out. 3ax plus 12ax, 15ax minus 6a. So we're left with the remainder, 15ax minus 6a over x minus 1 squared, because that's the same as that. I just didn't want to write it again. And again, we don't really care about this. We just care that this is our asymptote. And so we set a, why do I do this? Okay. So we know that ax plus 6a equals 1/2 x plus 3. So we can quickly see that a is going to equal 1/2 because we can just look at the coefficients of x. 1/2, 1/2. a equals 1/2, and there we go. And some of you probably saw that after just doing the first step of this, we saw that ax is the thing you multiply x squared by to get ax cubed. And we could have immediately just gone for that because the only x term in this, what you get when you divide is 1/2. So you can immediately see a is equal to 1/2. And if you saw that, then good job. Saved a lot of time, but I just wanted to go through the whole process because again, this is how the asymptote relates to the function. If you have something that's not, where the asymptote isn't y equals 0 or y equals a constant. So just make sure you understand why this works. And this is kind of why I wanted to talk about this problem. This is what's unique to it with the way the asymptote works and kind of reverse engineering the way that you do it. So again, we have 1/2, and that works here. And if you do it either way and you see there are multiple ways to do it, a good idea is to check. And like if you've done it this way, do it this way real quick, or if you've done it this way, do it that way, because you never know when you're going to run into an arithmetic mistake like I did up here. So just be aware of that, and that's it.